Got 44.18. I got this 113.05. What do I know about this guy right in here?
So I got
180.
See, I'm seeing it. If I took this as a straight line
180.
and 180, right. If this was 180 and I subtracted 44.18 and subtracted 113.05, I'd get, would I get that missing angle in there?
this to see.
Okay, see it?
It bothers me. So it's 180 minus 113 minus. I don't know where I got that angle. So for the angle,
2237, man. Yep, 2237.
yes.
Uh huh.
Can't get that.
2237.
Damn, I thought I was doing.
And again, I know I have to try to keep lightening the load and lightening the mood. Just think of it as a puzzle. That's all that is it's a puzzle of 180 degrees and what's the missing angle. That's really all you're looking for in each of these is just what does it give me and what's missing.
Isn't it 2273?
Did you do it in decimal by chance, Manny?
That's in 4418 in the decimal.
4418 is a degrees in a minutes. Right? 44 degrees 18 minutes?
Yeah, you're right.
Try it as minutes.
How do we figure for the 4418? Where did we get that? Oh, never mind. I see it. It's the 44. That's the bearing.
291.13. And double check. Howard, do you guys like that 2237? Did anybody match that with me?
Yeah, 226.
As a 22 as a decimal? You're punching it again here.
Yeah, the
Oh
decimal.
man, this piece.
So if I had 180.
It should be 37.
Yeah, I think that's okay. I think
Yeah,
2237. If you
it
add
is.
all three of those up, you should get 180. 113.05. And it's degrees, and it's a degrees minutes. Manny, that's why degrees minutes and not decimal degrees. And let me make sure my north and west, because I might have a wrong number in there. $68.47.
Yeah, I got 22.1637.
In decimals, so
Oh, so okay, you got it.
degrees minutes, yeah.
Okay. 0.1637 times 60.
Yeah, I still got the
920.
22 or 22 and 37.
How'd you get that?
I just want to work off file if you want to check that.
Maybe my decimals are wrong when I do this. So I did 5 divided by 60.
So you did it too.
Oh, see, you got 0.832. That's you had point. So do you did 0.5 divided by 60? 0.0. To
But
get that.
It's this, yeah.
So you 0.05 divided by 60. No,
This, I converted this into decimals.
Oh, okay. That's what I did wrong. I copied that one. Okay, that's wrong. 208, 83. Uh-huh.
13.
Okay, got it. Clear. Two point six. No, I still give her. So this one.
Yeah.
Oh,
so
okay,
to the
that's right,
point
that's right.
67.
And then, yep.
6167 times 60, and then it should be 37.
37.002.
So it's just 22
.03
degrees and then 37.
minutes, yeah. But to find this, that's
So
what,
to find that, oh, give me a sec.
How's everybody coming along okay? Anybody got any different numbers?
find out once I get them.
Yeah.
So this is, sure.
224.18. The reason I'm quiet over here is because I'm just working the numbers myself, just to see if everything is checking on my end.
What'd you get for your estimate for that? 291.13.
Because something's not working on my end. 224.
How often do you do like this whole thing like at work?
Do you want me to answer that honestly, or should I just kind of tell you like a cool
Honestly.
answer?
So what you're telling us is we shouldn't need to know this.
Once we get to the easier to the dissection, Manny, we're not going to use this in industry, and this is really interesting. All right, you guys ready? Because Bob's human.
Figure it out.
Okay, you ready? Watch this. You ready? Uh-huh. Okay.
Uh-oh.
Okay. So what if I did that, because Bob's over here working numbers as well too, and Bob's looking at his cribs, and Bob's not convinced that 224.18 is necessarily that angle. So let's cut that one up a little bit here. Let's cut that one up. What is that? What is that angle? Let's see. Did Bob have it right? I didn't do this on purpose. This is not a trick question, by the way. Let's check this out here real fast. So what does the 4418 represent? That's the south to the west, right? South to the west. Is that this angle right in here?
Mhm.
It is, right? So if this is 44 degrees, 18 minutes.
And the opposite one.
So that means, is this one here, that 4418?
No, it's underneath.
Mm-hmm, right?
Whatever. It'd be the 15.
It's the opposite, right? It's going to be this. What's this here? 4418, 90, it's 90 minus that, right? So if I was to find this angle here, what is that, 90? Minus 44.18. 45.42, Gabby, is that what you said? 40.
Oh, that was close.
45 degrees. Gabby, I'm liking it. I'm liking it. So that's really 45.42. 30. I got 45.42, Gabby. What'd you get?
42.
42?
Yeah, I had that right.
45 degrees. 42 minutes. I like Derek saying, I had that right. I wasn't getting this bearing over here. I was working my numbers and I was not getting that bearing. So here's what I'm going to do. Because erasers, that's why we work in pencil. So what is this in here? What's this interior? It's 180 minus this, right?
I originally had 20 something, 20 point something.
How about 21.13? What are we thinking? To err is human, even when you're the guy sitting behind the projector screen. So that's what I did. I made the error of just taking the forward azimuth and using that angle.
Is it 21:13?
21 degrees, 13 minutes. Yeah, everything I'm doing here for the most part is in degrees and minutes. Because then to get the bearing, what we want to go in this direction. We're heading from here to here, so we need this interior angle here. So this is what, 90 minus 2113. 68.47. 68.47 minutes. And then if you want to jot it down, there's our last. That little sliver is a real slight tip.
47. Yep. 68.
North 7 and 21. All right, so I'm going to drop into the table. Let's finish. We'll get this new set of data. I'll just give you that last one, that 721 there. So let's do this real fast. Let's just put these in decimals so they're easy to go in our calculator. 68.47 is what? $68.7833. So with those decimal angles, let's go ahead and just throw them, do the same calculation. Use the use the cosine for our latitudes and the sine for our departures. Let's finish in these last calcs here. So just taking the cosine or the sine of the angles.
Oh, never mind, I was looking at the wrong one.
Okay. All right, so even if you're not running the calcs out, you can just kind of cheat off of me. We can take a look at the tables. And let's kind of walk through what we do with the data. And we're gonna end at this point. So not end, but this will be enough. This will be enough traversing for one day. So if we get all of our numbers, let's take a look at what these numbers on our sketch of my pan out here a little bit. What they represent. Out a little bit. As far as I go. Let's try that. So what do each of these numbers represent? Well, what we said is our latitude column is our ladder. That's our ladder. Ladders are what? Up and down. So the latitudes are the distances that we all measured in this up and down direction. Let me go to this cleaner sketch here. Now you'll notice in the top column headers, you see a plus and a minus. You see that I put a plus and a minus, and a plus and a minus. A plus for a north and a south is a minus. Now why do you think we're doing that? Well, when we said we need to go around this shape, we started at A and what? We went in this direction. We went north, so north is a plus. If you look on the table, we show north as a plus. When we come back to go south, so from B to C is in the south direction, we've got a minus. So our bearing on this one was north to east. This was what? South to east. This was also south to west. So the latitude, the ladder, we're heading south. We're heading south, right? We go from D to E, we're going north, and we're going north. Here's how we use the plus and the minus. We look at our bearing, and we say we're in the north direction, so we went plus, we went up. For B to C, we went south. South says minus, so we went minus. So let's keep doing that. South bearing, this was a minus. When we went from D to E, we were heading north, so we headed back north as a plus. We've got a north and a plus. You guys see how I did that? Mm-hmm. We're just following the direction of whatever the bearing says, we're going to use that sign. So same thing with the east and the west. We went from here. So this first one, we went in the easterly direction. East, east. East is a plus. So east is a plus. East is a plus. These three guys right here are what? West, west, and west. So west says make them negative. Negative, negative, negative. So what did we do? We said this is how far to the far east we went, and then we had to come back and west. So what do you think happens if we add the columns up? So we're adding the total distance of how far we went one side and how far we came back the other. Add those 5 numbers up, both the total of the north and the total south. Let's see what we get. 0, 1, 2, we got many? I got 0, 1, I got 0, 1, 3. Oops. There we go, 0, 1, 3. So 1, 2, 3, 1, 3. How about the other, let's try the other column. So let's do the departures. Oops, can't do it. .11 feet. What everybody gets for the sum of the departures. Is what I got. Notes straight out of Bob's crib sheets. So what does this mean? This means that when we ran our traverse and we took all our shots, we measured all of our angles. We tried to see which direction did we miss, how far did we miss. This is how far we missed. So we missed by 0.13 feet in the north-south direction, and we missed by 0.11 feet in the easting direction. So we did pretty good. I mean, relative, right? But how good did we do? What should these be if it was perfect?
0.
0, exactly. And it's not 0. So this is that little bit of incremental error that's inside the traverse. So let's look at our formula sheet. We've got a couple of factors, and these are presented in the book. We can determine, or at least assign a factor, I'll just find the page so I can reference it, of how good did we do. So when we have a factor, you look on the crib sheet, you'll see the term called the linear error of closure. Linear error closure pretty much says how good did we do. If we run the math out for that formula, and it's what? The formula is we take the square root of the squares of that error that we had. Let's plug this in real quick here. I'm just going to throw these in. So we had some of our latitudes was what? 0.13? 0.13 feet. And our departures was minus 0.11 feet. So if we square them both, take the square root, kind of looks familiar. Does that kind of look like Pythagorean's theorem, maybe? Kind of. That's kind of what that is. It's just taking a triangle. Tell me what you get when you solve for that. 0.17. I'm going to find where those factors are at. There we go. Okay, we worked that out for our particular, we get 0.17. And that's in feet. So that says in the north direction and the east direction, if we went all the way around this traverse, we were 1700ths off. 1700ths was our, how far we're off. So that's one formula. It's not too bad. Think about this. If it was 1700ths and we went from U building back to here in that little traverse and it was 1700ths, that might not be that good. If that 1700ths was from here to Hobolt Road and back, it's probably pretty good, right? So if you look at the next factor on here, we have what's called the precision, and that's on sheet 190. So if you look on page 190, I think 190 is the calculator, it's actually 192. What the precision says is, well, how big was this thing? How big was our traverse? How big was the traverse versus what was our error? So it's a factor. So if we were to say that the linear error of closure, and the precision is defined by, it's the linear error of closure divided by the entire perimeter. It's a factor. How big was our error compared to how big did we do? So if we plug this in, let's just run this formula out real quick here. So if I was to say that the linear area of closure is 0.17 feet, what's the total length of the perimeter of the traverse? Let's go back to the table. So this is our total length. What do we get if we add this whole length up? How big is it? How far did we go? So if you add these 5 up, what do you get? I'll do it for you, but you can punch it all in there.
559.36.
559.36. So how can we use that factor? So we're saying we were 0.17 feet off in our total going around the traversing distance. If we divide that by 559.36, what do you get? Probably something really, really small. Something really, really small, right?
Yeah.
0, almost you gotta change your calculator factor. It's really, really small. 0.0003 is the number. All right, what can we do with that? I'm gonna show you guys this in the book. And when we talk about surveys, let's look at this off of page 190. So 190 talks about how accurate, how precise could a survey be? How good should we be? And they've got 3 factors in here. So if, for example, the ditch survey's 1/3,000. We're gonna talk about how we convert back and forth. So ditch survey 1/3,000, a monorail 1/7,500 or 1/10,000. Control survey is like 1/30,000. What's the significance of that, Bob? I don't get it. So on my little cheat sheet here, that's what we've got. So if we were just working in construction, we can be kind of accurate. But Bob, I don't see it. I've got this little tiny factor here, but I've got this over here. We're talking about a ratio. On your calculators, do you have a 1/x function or an x to the -1 function? It flips. I know, Sam, I think I looked at it yours. Did I, Crystal, did I look at it yours? Yeah, you should see an x minus 1. Basically what it is, it's
yes.
1 divided by that. If you take this number and just use your 1/x function or your x minus 1 and just flip it.
Is it x to the negative first power?
Yes, you might see it on your calculator as x to the -1. I mean, I can show you on mine, it's this 1/x button. It's basically taking 1 divided by the number that you just got. See if you guys see it. Does everybody got your function? I'm just looking. Gabby, Crystal, Manny, you guys okay?
Yeah.
Right?
Oh, okay.
Mm-hmm.
So if it flips it around, I got 3290. So it's basically 3300. And we can look back in here. That's what this 3000 represents. It's basically saying it's the inverse of the 003. So this survey, 3290 was our ratio. It was construction level. So even though we think that 0.17, which looks like that, over 500 feet doesn't seem like a lot, we didn't do that good. It's good for construction if we needed to build a ditch or a manhole or something, but we would really want this error of 0.17 if we were going to do something for a building pad or something, a control survey. That would have to be even smaller than that. So that's what it is. It's 2 factors. You've got the linear error of closure, and this is the precision. So for what we did and the numbers we ran, the shots we took to come up at 0.17, our precision was okay. That's it. Just kind of see how that works. It's basically a ratio. That's what we're looking at on the table here is a ratio. How did these 2 errors and the total perimeter, how good did we do? Okay. I think that's plenty.